Let's try to imagine what happens if we take a set of k vectors that's linearly dependent and add or remove vectors from it. Now, remember that independence or dependence is a property of the set of vectors, not the individual vectors themselves. So if we start out with a set of k dependent vectors and add another vector to it, well, it's still going to be dependent, because one of the vectors in this set can still be written as a linear combination of the rest, regardless of the extra vector we've added. If we remove a vector from this set, we might get a dependent set or an independent set. We really have no idea. Finally, if we have an independent set and we remove a vector, well, the remaining vectors are still going to be independent. The basic example of a linearly independent set consists of k vectors that are non-zero and mutually orthogonal in R to the n. So we're using the idea of a scalar product now. It's not very hard to prove this. So let's take the first definition of linear independence. We have this equation that we want to solve, that a linear combination of our k vectors is equal to 0, and we're going to assume that they're all orthogonal to each other. Well, we can simply dot both sides of the equation, or take the scalar product of both sides of the equation with each of the individual xi's. So on the left-hand side, we have that x1 dotted into x1 multiplied by c1 is equal to 0, coming from the left-hand side, which is always 0. Since the norm, or the length of x1 is non-zero, the only solution to this equation is that c1 is equal to 0. And we can keep going. So we take the original equation, dot it one by one into each of the xi's, and find that each of the coefficients has to be 0, which then proves linear independence. I don't know exactly how to motivate that. It should be obvious. The basic example of so on the right-hand side, we have x1 dotted into x1 times c1 is equal to 0. Did I just say the right-hand side? Fuck.